In this section, we will introduce a new machine learning model, decision trees. Decision trees are some very popular machine learning models, and we can easily interpret and understand them. In this section, we will use some examples to get things more clear. Let's start with the first example. We have this package delivery prediction problem. In this problem, we are going to use three features such as weather, demand, and address, and then we will try to correctly classify these data points as being late or on time. Let's fit a simple decision tree on this dataset and try to explain the process. When we are fitting a decision tree, we need to select some features. As our first feature, this tree starts with the weather feature. And then we will look at what type of values that feature gets. This feature becomes sunny, overcast, or rainy. As a next step, we partition our data points using these values. In this case, we get data points with the sunny, overcast, and the rainy. As a next step, we are going to look at these data points, but focus on the target. If we see a single class in the target, it means that we actually classified them correctly. And in this case, we can stop the tree there. If we see some mixed values there, it means that we need to keep growing. And in order to grow, this time we are going to select a different feature. For example, here we selected demand and address features and kept growing the tree. Let's also explain these nodes. In our tree, we started with the weather node, and this is the root node because we started the tree with this. And we also have these internal nodes. For example, they use the demand and address features. These nodes are used to grow the tree even further. As I mentioned before, when we classify things, we call them leaf or terminal nodes, and this is where we stop the tree. We don't grow any further. Let's put this into an algorithm. The algorithm is called ID3. With this algorithm, we select the best feature and then split the data points with that. And after the split, if we see a single class, it means that that's a leaf node. If we see some mixed results, it means that we need to keep growing. So we can go from 3 and again to 1, 2, and again from 3, 1, 2, and keep growing the tree like that. This is called the ID3 algorithm. Alright, we just explained the simple decision tree on this sample data problem. In our sample problem, we had these categorical variables. So what happens if we have some numerical features? In this case, we are going to have a different example for that. In this example, we have these numerical features, x1 and x2, and we have this target y, which can be either 1 or 2. Let's also fit a simple tree on this. Let's plot the data. It looks like this. We have class 1 and 2. This time, in addition to our feature selection, we will also select a threshold. For example, here we selected the x2 feature, and we use this 5 as a threshold. And as you see, when I use that, I see that for the data points that are larger than 5 with the x2 feature, I have class 1. For the rest, I have some mixed values. So for the rest, I keep growing the tree, but for these guys at the top, I stop the tree. So this is a leaf node. So for the second part, I will keep growing the tree. This time I use a second feature here, x1 feature, and I also select a threshold for that. And this time it results in some pure results, for example here, and also some mixed results, which are here. So this means that I still need to keep growing one more time. I correctly classified all the data points. How do we select the best features? We will look at the uncertainty or impurity. We want our features to give us some pure splits. Let's take a look at this example. Here we are using the weather feature. Before the split, we had 9 positive and 5 negative. So this is very impure. There is a lot of uncertainty here. Similarly, after the split, we are going to have some type of different distributions. Here with the sunny, we have 2 positive and 3 negative. Again, this is not too sure. With the overcast, however, we have 4 positive and 0 negative. So this is absolutely sure. This is absolutely pure. With the rainy, we have 3 positive and 2 negative. And again, this is not too sure, and there's a lot of impurity again here. And we are going to do the same thing with the other features, with the demand and address. And overall, everything looks like this. Although this is cool, we still actually didn't quantify how uncertainty or how impurity arises from these splits. For that, we are going to use a mathematical function. So this function is called Gini impurity. And this function allows us to see how much impurity we have at a certain distribution. So let's take a look at these examples. Assume we have these 2 classes, negative and positive, and we have these 3 different distributions here. In the first distribution, we have full negatives. Everything is negative, so there is no uncertainty here. In the other one, we have full positive, only the positive samples. This also means that we have low uncertainty. And this function, when we calculate it, this gives us 0 uncertainty. On the other hand, when we have 50-50 distribution, over here this gives me the highest amount of uncertainty or impurity. So this function works. But how do we calculate these numbers? We will also have an example for that. Before we actually get to this calculation, let's also talk about this information gain. Information gain is the expected reduction in the impurity. So we want our features to have some good or high amount of information gain. So we calculate the impurity before the split and after the split, and we want to have a large number. Let's calculate this Gini impurity. In this feature, before the split, we have this much impurity, again using the impurity score. After the split, we have these distributions, 2 positive, 3 negative. I can calculate it like this. This one is 0. And this one is this much. As you see, when we plug in numbers, actually, for the overcast case, we have 0 terms. And because of that, this multiplication becomes 0. And this is actually the expected result because this is absolutely pure. So it means it should be 0 in terms of impurity. And overall, we are going to look at the weighted sum of these impurity scores. So when we do that for the weather, we see that it's 0.34. And let's calculate the gain. Impurity before the split, impurity after the split. This gives me 0.12 gain. Similarly, I'll do that for the other features. For the demand and address, I make these calculations and I look at the information gain. And overall, I make my selection based on the highest number of gain. And it comes from this weather feature, and that's the feature that I will be choosing. And for that reason, actually in our tree, weather is the root node. And here's the summary of the ID3 algorithm. We select the best feature to split. We separate the training samples. If we have some pure results, we stop and call it a leaf node. If we don't, we will keep going. If for some reason we actually need to stop, for example, this can be some type of tree parameters, for example, the depth of the tree, or maybe the maximum number of splits, or maybe the maximum number of iterations. When we hit that number, in this case, if we have to stop, we assign the majority class for that node.